This example is on the design check of a column. This is a Glulam column, and this Glulam column has combination 4 as for the layup, and it's a Douglas fir column, so it's a softwood column. Okay. We are going to assume that it's normal conditions, so dry conditions, and normal temperature. So dry conditions, that gives us information on the CM, the wet service factor, which is 1.0, and the C sub T is 1.0 also, which is normal temperature. This is the only example in class. We'll be working with LRFD. Overall, similar process for column design, but I'll just take you through the steps. And for LRFD, we're assuming that it's 1.2 times dead load plus 1.6 live load combination that controls the design. L is for occupancy, so that gives us information about what CD to use for our design. The other thing, it's LRFD, and if you go to table 3.3 of the NDS, the main book, you'll see that lambda is 0.8. Okay, so those are the main factors that we need here for our design. Moving on, and whenever we're doing a column design, the first thing we need to do is to determine what P sub U is. And here we're going to do our example assuming that we can compute P sub U, meaning what is the load that it would take. But here, instead of the design check, we're estimating what is the maximum load that you could ever consider for this column that has a length. This is the length of the member is 14 feet. If you actually multiply by 12, that gives us 168 inches. And here is our section. X is going to be the strong axis dimension here, and we'll use Y for our weak axis dimension, which means that the depth of the member is going to be 10.5 inches. That's that one there. And about the y-axis, so the distance in the x direction, that's going to be our breadth, and that's going to be 8.75 inches. Okay. All right. Whenever we're doing the computation of the maximum load that we can take for P, or so maximum axial load, be it sawn lumber or be it glulams, be it ASD, be it LRFD, the process is always the same. We have those 4 main steps, which first we need to compute the adjusted value, accounting for the Young's modulus and really the Euler buckling strength of our column. Then we need to compute the adjusted value except for CP, that's the FC star. It's the strength or capacity based on FC star. And then we combine those two to compute our C sub phi, our stability factor for columns for axial load. And ultimately, that's where we determine our adjusted value for the strength, FC prime. So we always need to first compute the buckling stress, then the FC star, then we compute our stability factor, and then we combine those, FC star times the stability factor, to get our capacity. That's the stress capacity. We multiply by the area of our cross section, and that is the maximum value that we could design our column for. Okay, maximum load, maximum ultimate load. It's also what we've called our ultimate axial load. Okay, so those are really all the steps we need to consider as we go through this. So I'm going to move this here to the left, so I have room to write over here, but really those are the steps that we're going to be working with. Okay, and just to give me some room, I'll just clean these here for us to work on this problem. All right, so for f sub b, I'll write here the equation for you guys. F sub b is given by 0.822 times the E min used for stability calculations, because that's to check our stability of the column, and then divided by the square of the slenderness ratio. And the slenderness ratio is just LE over D. Okay? So in this case, because the buckling length is 14 feet, L sub E is 14 feet, and we want to get the minimum stress that's computed here, the minimum buckling stress. I'll use D, actually not the number that I had written here, but I'll use the smallest cross-section dimension, right? So D, whenever we're plugging into this equation here, D is, for FCE, is the smallest, the least section dimension. So even though when we're looking at beams, this would automatically, the smallest section would be the breadth, and that would be B, and D would be the 10.5. When we're doing for columns, careful that this D is always the smallest dimension of the two, all right, especially for the same buckling length. All right, so with that, what we need to do is we need to go get our E min and our reference line. So for our E min, we're going to get that from table 5.5, sorry, table 5b in NDS. And so I'll jump over NDS supplement. We are looking at NDS supplement. This is page 67 of the 2018 version. Because we're using Douglas fir, I'm just going to double check. This is table 5b. It is softwood, so table 5a and 5b are for softwood Glulam members, so that's great. We're in the right place. And we have a 4, visual grade 4 was our combination symbol. Visual grade 4, Douglas fir. That means here's our grade, number 1. But really what we're focusing now is the axial load for stability calculations, the minimum number, and it's 1.0. If you actually zoom in, it's 1.0 times 10 to the 6 number. Okay, so going back, 1.6, sorry, 1.0 times 10 to the 6 is the number that we're going to be using here, and that's in PSI. Then from table 5.3.1, so that's in the main book, let's go to that one. That's this table here. I also have what factors to use when we are looking at the reference value for E min. Okay, so the reference value is the one that we just looked up in our table, and then for E min we need to multiply it by C sub m, C sub t for temperature. And because this is the only example we've really looked at LRFD, so LRFD, there's these two other factors, the K sub f and phi, that we need to multiply to come up with our adjusted E min. Okay, so if I go back to the problem we're working on, I'm using the green pen, and so I can compute the adjusted value of E min, which is just copying over from table 5.3, E min, C sub m, C sub t, and then we have those two other factors for LRFD, K sub f, and our phi factor. So what was E min we had there in blue was our 1.0 times 10 to the 6 psi. There's no CD here, just C sub m, which was 1.0. C sub t is 1.0, normal temperature conditions, and then 1.76 and phi of 0.85, which was the numbers I circled for LRFD, 1.75 and 1.76, right? Let's check. NDS 1.76, yes. So here it's 1.76 and 0.85. Okay, so multiply all those together and we get that our E min adjusted value, so prime, E min prime adjusted value is 1.5 times 10 to the 6 psi. Okay, so table 5b and then table 531 for us to compute this E min, which is the reference value here for FCE. Okay, so you can plug in those numbers now. 0.822 times 1.5 times 10 to the 6 psi, all of this divided by our length, which is 168 inches. That's the restrained length for buckling. I'm going to divide that by the smallest number, as I had mentioned, 8.75. All of those are in inches, so that's okay in terms of units. And that gives me FCE of, I forgot it squared here, 3.345 psi. Okay, so that's our first one there. Now I got to compute FC star. All right, FC star. For that one, FC star is everything except CP, but we can still go back to table 531 in the NDS supplement. Now we're focusing on F sub C. So for F sub C, here we go. I have CD, CM, C sub TT, and all of those have to be multiplied by the reference value in compression. These together, so the product of these gives me FC star. If you go back to the lecture where I first talked about this, that lecture 17, that's really only FC star here. It does not have CP. CP we plug it in later. Okay, because it's LRFD, really we have to combine for FC star. We have to combine all of these here. So ASD would only be CD times CM, CT 2.4. Then that's next. ASD only, we have a CD factor. LRFD, we have the gamma factor. Okay. So Cm, C sub t, Kf, phi, and lambda. So moving back and plugging in our equation, so I'm going to have our reference value F sub C, then moisture, temperature, and then our adjustment factor to go from AST to LRFD, phi, and lambda. All right. And so if we're going to start with this, C sub F, sorry, F sub C, that's in our NDS supplement. Four or more laminations. And our number is 2100 psi. All right, so lecture 21, let's go back and compute here. So 2100 psi, and then C sub m was 1.0, C sub t 1.0, K sub f, so that we already saw that number in table 531, which was 2.4, 0.9, and the last number we have here is 0.8 for lambda. All of that together gives me 3629 psi. And this is when you guys see that I'm also always making these small mistakes. psi. Okay. So I can now compute C sub B, CP, sorry, the column stability factor. I've just computed these two steps, and I need to compute C sub P. So for C sub P, I'll write the simple version. These are a lot of factors, but really you have three factors that you need to get into C sub P. One is factor A, and then this same A goes in here, A squared minus B over C, where A, this factor A, is 1 plus B over 2C. Factor B, if you look at the equation that we had before, and we've done an in-class problem with that, we have, it's our FC for stability calculations divided by FC star. And C, that other factor that goes in there, C for glulams is just 0.9. You may recall this was 0.8 for sawn lumber. Okay. All right, so B 0.92. B, I'll go back up. So this was 3,345 psi. And we had 3,692 psi. And that gives me 0.92. And A, now I need to plug in B and C. So that's 1 plus 0.92 divided by 2 times 0.9. And I get for A 1.07. Plug all of those here on the left. And now CP is going to be 1.07 minus square root of 1.07 squared minus B, which is 0.92, divided by C, which is 0.9. And that gives me CP of 0.72. Okay. So now, if you go back to my little cheat sheet here, I have FC star, CP. I can compute the actual adjusted value of FC prime. And so for FC prime, which is the adjusted value for compression strength, it's just going to be FC star times CP, which is 3629 psi times CP that we just computed, 0.72, and it gives me 2612 psi. So our final solution here, P sub u, our ultimate axial load, has to be less than or equal to FC prime. Let's clean that up a little bit. FC prime times A, and A is just the cross-sectional area. For glulams, we don't have to look up tables for that. And so FC prime is 2612 multiplied by the area, which is B times the 8.75 inches times 10.5 inches. And that is the maximum number that we can use, okay? So P sub u has to be less or equal to that product. So that was it. Glulam column LRFD. We went through it. We had a lot of steps, but really it comes down to this here. I'll just rewrite that, which is we have to compute. Can I delete it? We had to go ahead and compute first our FC sub E and our FC star. We combine those two to compute C sub P, and then ultimately we got to our adjusted value of the strength multiplied by the area, and it gives us the ultimate load.